Hello, welcome to nonlinear pharmacokinetics. We're going to first start out by introducing the ideas here. I'm not going to go through the objectives, but you can. So after 2 weeks on 300 milligrams a day of phenytoin, the measured concentration of phenytoin is 4 milligrams per liter. The target therapeutic range is 10 to 20 milligrams per liter, so it's low. So the physician thought, all right, I'll double the dose rate. So they were getting 300 milligrams a day. So if we go up to 600 milligrams a day, the concentration should go from 4 milligrams per liter to 8 milligrams per liter. It's still lower than the therapeutic range, but he didn't want to overdo it. So, or she, I don't know which. So 2 weeks later, the patient calls the pharmacy with complaints of double vision and difficulty walking. If you have studied phenytoin, you'll know then that these are common dose-related side effects with phenytoin. So the physician said, hold the phenytoin and let's go see what your level is. Had a concentration drawn, and then rather than it being 8 milligrams per liter as they predicted by doubling the dose rate, it was 36 milligrams per liter. Yikes. What could have caused this? Well, normally we know that there's a proportional change in your concentration with dose rate, right? Because normally, I'm going to change the color. Normally, CSS average is equal to the bioavailable dose rate of the drug or the drug in over the clearance or the drug out. And we know that if bioavailability and clearance remain constant, which they should in normal circumstances, then our dose rate and CSS average are going to be proportional, which is why the physician thought if they double the dose rate, you're going to have double the CSS average, and that is usually what occurs. But if the assumption that the bioavailability and clearance remain constant is not true, then we have a problem, right? And in this case, since the CSS average was so much higher, it's either because the bioavailability was increasing or the clearance was decreasing. So instead of doubling the dose rate causing a doubling of the CSS average, it increased by 9-fold. Yikes. So this is phenytoin is kind of famous or infamous for its nonlinearity, and the nonlinearity is due to a saturation of the liver enzymes that are responsible for clearing the drug. And therefore, as concentration increases, clearance decreases. And that ends up being a loop, doesn't it? So this is called nonlinear or dose dependent. It is also sometimes called capacity limited because we are overwhelming that capacity of liver enzymes to metabolize the drug. So the interaction of the drug molecules with a limited number of sites gives us a saturable system or a capacity limited system. These are all Michaelis-Menten type relationships. So nonlinearities are always due to Michaelis-Menten relationships. As you remember, Michaelis-Menten for hepatic enzymes is Vmax. Intrinsic clearance is equal to Vmax over Km plus concentration. So the key is this concentration term that's in here. So for anything to be nonlinear, it has to be it's usually Michaelis-Menten, and there's a saturable capacity limited process. So how do you recognize a nonlinearity? Well, we know that dose rate and CSS average should be proportional, right? So CSS average is equal to bioavailable dose rate all over clearance. So if bioavailability and clearance are remaining the same as they should in linear situations, then your CSS average and dose rate are going to be proportional. So if you double the dose rate from 500 milligrams a day to 100 milligrams a day, we would expect the CSS average to go from 10 milligrams to 20 milligrams per liter. And it does here, doesn't it? So this is linear, isn't it? So that follows what we would expect. Now, how about here, where we go from 50 milligrams a day to 100 milligrams a day, but instead of seeing 10 to 20, we see 10 to 32 milligrams. So this is higher than what we expected, right? So therefore, if it is higher than what we expected, then either bioavailability has to be higher or clearance lower than expected, and it is probably concentration dependent. Here's another example going from 50 to 100, and you go from 10 not to 20 but 13, so this is lower than what was expected. So in this case, CSS average, bioavailable dose rate over clearance. Again, we expect those to remain the same, but in this case our CSS average was less than what we expected. Therefore, clearance must be increasing with increasing dose, or bioavailability decreasing with decreasing dose. So this equation is important. The other one that we often use is area of the curve is equal to bioavailable dose, not dose rate, but dose over clearance. You can see they're very similar, because CSS average is actually equal to area of the curve divided by tau, so they're the same thing. So if you divide these both by tau, all right. What are the sources of nonlinearity? Well, you can have nonlinear fraction absorbed, nonlinear fraction that escapes the gut metabolism, nonlinear fraction that escapes the first pass effect. This should be FH, sorry. You can also have nonlinear binding. So if you have nonlinear binding, you're going to overwhelm these binding sites. You can also have nonlinearities in clearance. We've already talked about the fact that you can overwhelm those enzyme systems. So there's nonlinear intrinsic clearance. Recognize these are all Michaelis-Menten, aren't they? Binding, Michaelis-Menten. Renal, we have filtration clearance, we have active tubular secretion clearance, and we have reabsorption. Reabsorption, remember, is passive, so this is not saturable. But active tubular secretion requires carrier systems and follows Michaelis-Menten, so therefore it is saturable. That's it for the first section. Thank you for paying attention.